Hi, my name is Laura Sales, and I wanted to share with you today some of our latest results on the formation of ultra-diffuse galaxies in galaxy clusters. As the name and the pictures here indicate, these are galaxies with extreme low surface brightness. And so before starting to explain what we have done, I wanted to give a sense of the scales involved in this study. So when we think about clusters, the closest structure that we have to the local group in this image is over here in this blue label. So the closest cluster would be the Virgo cluster, which has an intermediate mass of virial mass 10 to the 14. So although it's not really one of the massive clusters or galaxy clusters, the modest mass is overcome by how close it is to us. And so it is a very interesting environment to study these dwarf galaxies. So the distance of the local group or the Milky Way to the Virgo cluster is somewhere about 16 to 17 megaparsecs. Another structure where ultra-diffuse galaxies have been surveyed is in the Fornax cluster, which is down in the southern hemisphere. And perhaps the most, I don't know, a common place or one of the most famous places where ultra-diffuse or UDG galaxies were studied is in the Coma cluster. The Coma cluster is 100 megaparsecs away from us. So remember, Virgo was 17 megaparsecs, so Coma is somewhere very far away, 100 megaparsecs. And this helps appreciate how difficult is the study of these very dim, very low surface brightness galaxies. So let's start by looking at the sizes of dwarf galaxies in galaxy clusters. So what you see over here is the scaling relation between the effective radius and the stellar mass. This is only observations. So it's a compilation of different observations. And so at the scale of dwarf galaxies, that for the purpose of this talk is going to be between, a bit more than 10 to the 9 and below. We have a large scatter, something that Jose also highlighted in his talk. And so what we can see is this median relation, for example, this line, a solid line here, it's indicated the median relation of passive galaxies. And scattered away from there, there is a population of very extended objects that have a low mass. So when they were, those are going to be our UDGs, although the criteria to define an UDG is not so clear. That's how they were first presented to us by Van Dokkum in 2015, with the impression that these are objects of the mass of a dwarf galaxy, right? So 10 to the 8-ish in general, around 10 to the 8. But the sizes, the half mass light or half mass or half light radius, more comparable to the Milky Way. All right, so the Milky Way will be somewhere over here. So that gives you, again, an idea of how diffuse these objects are. And the first hypothesis, the fact that they were so extended, but harbored so little mass, led to the idea that these UDG galaxies were failed Milky Way-like galaxies, galaxies that were destined to be as massive as the Milky Way, but somehow failed in forming the stars, but they had their dark matter halo be quite massive. So since the discovery of many of these ones in Coma and then in other systems as well, the key question has been how do these ultra-diffuse galaxies form? And also, what is their dark matter content? So quickly coming up after the initial discovery, of course, these low surface brightness galaxies have been discovered before, but found in so many numbers and with uniform properties, these UDGs. So we're going to talk about discovery of UDGs, although, of course, we have known that low surface brightness galaxies have existed before. So following the discovery of these UDGs in 2015, so certain studies observed that they were not only rare on how extended they were, but also they hosted a very large number of globular clusters. So you can see here two images of two different UDGs, and here on the right panel, changing the contrast, you can see these very bright white dots are globular clusters, or presumable globular clusters. And in a separate study, Peng and Lim also found, so different authors, you can see here the globular clusters are encircled, found that so they are extended, but also their specific frequency of globular clusters that is shown down here. SN is, for you, is just an idea of the number of globular clusters normalized by the stellar mass of the galaxy. So this is plotted against the magnitudes. This is bright galaxies. Dwarf galaxies tend to have, SN similar to more massive galaxies. Some of them seem to have an increased efficiency. However, these UDGs that are highlighted over here did really seem to stand out with crazy efficiency to form globular clusters. And since we believe globular clusters might be a good indicator of the virial mass or the halo mass of a galaxy, these high SN values were interpreted as supporting the idea of failed Milky Way galaxies. So UDG galaxies were a sort of framing to become so kind of a Milky Way comparable galaxy to the Milky Way that didn't really form stars. For some reason, they stopped. However, moving forward, the discussion diversified a little bit more to say, well, it could also be, the evidence is inconclusive, and it could also be that they are just hosted by dwarf halos. They are just simply the tail end. They are not a particular kind of galaxy, it's just the tail end of most extended dwarf galaxies, dwarf halos. And if that is the case, then it becomes more interesting because there are many more theoretical processes that can give rise to UDGs. And you have here some of the proposals that have occurred over time. Well, the first one was to say, for example, these very extended dwarfs are just simply the tail end of the highest spin dark matter halos. A very old, kind of an old idea where LSB or low surface brightness galaxies result from the high angular momentum of the gas. Following that, hydro simulations that had a particularly bursty feedback like fire or Nihao, they found in their simulated dwarfs that you could get this kind of very low surface brightness objects if you had this continuous, this breathing mode in the formation of stars that sort of heats up your stars, and you end up with a low surface brightness remnant. But there were also proposals of methods to form UDGs that were related to environment, whereas these previous two, the feedback or the high spin halos, refer to internal mechanisms that each dwarf halo might undergo. As they infall into clusters or groups, they are also exposed to other processes. And so tidal heating or the injection of energy in sort of pericenter passages was also proposed by several authors, and as well the tidal disruption of dark matter halos. But they, of course, with the galaxy inside, but they made the calculations in this work of Carleton et al. They made the calculation of tidally disturbing an NFW over a Caspi halo, and they discovered that it was not enough to explain all the numbers. So they claimed that you needed core dark matter halos. Now, the way to make progress on this very interesting topic is to observe more than a few, right? And so one of the first studies that aimed doing that is this one here, presented by Sang-Sum Lim and Eric Peng, in which we looked at UDGs galaxies in the coma cluster. This is HST imaging, and we identified globular clusters. And so because of this relation between the globular cluster content and the virial mass, you have kind of the chance of putting constraints of what kind of dark matter halos these UDGs will be living in. So the results are summarized in this slide, where you get, so over here on the left, you have the same plot that we saw before, the efficiency, the number of globular clusters per unit of B-band luminosity or stellar mass, as you can think better. That's what we call a specific frequency, bright galaxies, dwarf galaxies over here. And so the UDGs are the red symbols, and the normal or non-UDG dwarfs are in this combination of black and blue symbols. And so the first thing that comes or kind of highlights is like, oh yes, they do have very high specific frequency as it was found before in individual objects. However, may I draw your attention to the fact that there is a very large scatter. So although it is true that a lot of them have quite significantly high specific frequency, a lot of them are also very consistent with just the normal population of dwarfs, and some of them have 0 globular clusters associated to them. So this was one of the first, although not the very first, but one among the first studies to highlight the fact that UDGs present a very wide range of properties, and perhaps signaling to the fact that the formation scenarios might not need to be a single one, but perhaps a combination. So now you can use this scaling between the virial mass and the mass in globular clusters to estimate sort of a virial halo mass for these UDGs. This is the result displayed on the right. So the abundance matching relation over here by Moster, for example, or by Beruzzi are shown in the dashed and the solid line. And what you see is that the UDGs span, again, a very wide range of halo masses. So some of them are very dwarfish, almost outside of this abundance matching relation, or yeah, by that is well constrained. And then you have some extreme objects over here that seems to be living in quite massive halos for given their stellar mass. However, you see that we don't really get many objects on the mass of 10 to the 12 that would be a Milky Way mass halo. So the consensus is there is a wide range, but the consensus that is building, we haven't ruled really out many things, but it seems to be that it's more common or more accepted that these UDGs are actually dwarf galaxies. But you can see that these dwarf galaxies would inhabit a very wide range of dark matter halos. We can learn more from the dark matter content of these UDGs, not only by counting their globular clusters, but also by measuring their kinematics. And so when doing that, a big surprise appeared, and that was actually presented by the same team that put forward the Milky Way failed, or a lot of dark matter mass scenario for this UDG. So the Van Dokkum in 2018 published this paper highlighting this particular UDG called DF2, is because it's a satellite of this NGC, which is a big elliptical. This is not comma. This is actually a sort of more group environment. And so for DF2, they identified about 10 globular clusters, and they measured a very low velocity dispersion. And this very low velocity dispersion was interpreted as a galaxy that is lacking dark matter, complete lack of dark matter. And the interesting thing was that is not only the only one in the same sort of group. There is a second one, DF4, which has a velocity dispersion even smaller. Once you discount all the systematic errors, you get an intrinsic velocity dispersion of 4 kilometers per second. And for DF2 is similar, between 8 or 6, depending on what do you actually assume for your errors. So of course, these are extreme objects, and what happens is we decided to look at a more comprehensive sample of UDGs, and this is in the Virgo cluster again. And so this is in collaboration with Lisa Tolova, and we use Keck, DMOS to get the spectra of this particular, they are highlighting here 4 UDGs in Virgo. And you can see over here, these are all the things that we targeted, and the red ones were the confirmed globular clusters, and that were associated, presumably associated to our dwarfs. And so you can now study the velocity dispersion of these objects, and you come up with a plot that looks like this, where you get the radius, and this is the velocity, circular velocity, once you have transformed your velocity dispersion. So our measurements are these red objects over here. And so for comparison, there is what the velocity is expected for a halo like the Milky Way that is in this upper curve. And this is a dwarf halo of 10 to the 11. And so what we learned is a couple of things. First of all, in the very inner regions where you can actually constrain these kinematics, the difference between a halo of the Milky Way and a dwarf is not really that big. So there is a desire of sort of moving outwards in your tracers, so you can constrain the mass a bit more in the outskirts. But also we learned that some objects can be really outliers over here. And I want to highlight this. This is our VLSBD. And perhaps go back to the picture of VLSBD, which is here. And if you squint, you can see that it's quite elongated. And over here, you have the blow up of the same dwarf. And you can see definitely that is sort of it's elongated and pointing upwards, and is presumably undergoing tidal stripping. And interestingly enough, the globular clusters members, that remember that these red circles seem to actually follow the light distribution quite well, sort of confirming their association. So at least for one of our objects, it seemed that tidal disruption could be modifying or impacting the structure of this particular galaxy, something we will come back to later. So then we tried to see what we could do from the numerical simulations point of view. And we decided to look at this using full volume simulations like Illustris or Illustris TNG. Because we were interested in the formation of this in clusters, we found that the box of 100 megaparsecs gives you about 10 to 15 clusters of the scale of Virgo, and it was a good compromise between resolution and variety of objects. So the results that I will present in what follows are going to concern both Illustris and which is over here, is a bit older simulation, and the rebumped Illustris TNG 100, which was different initial conditions, but the same code and a sort of recalibrated or adjusted baryonic model, but all in all quite similar. So what you have over here is a picture of 9 of our Virgo-like galaxy clusters. In this case is Illustris TNG. So just for you to get an idea of the kind of objects that we are looking at. And so what we are going to do here is to try to study the dwarf population, and in particular, the one that is what would be classified as an ultra-diffuse galaxy. However, the first problem that you encounter is that if you look in Illustris or in Illustris TNG to the structure of dwarf galaxies, you will find that they are really not very realistic. They are all sort of too extended. So if you plot the mass-size relation of Illustris or Illustris TNG down to 10 to the 8 or about 10 to the 8 solar mass, what you will find is that all the dwarfs are UDGs. So then we clearly could not really trust the structure coming out from the simulations, but we do have confidence that the orbital dynamics and the dark matter distribution of these objects is relatively well constrained. So what we did is we're going to use the Illustris TNG, in this case, information and clusters, but we are going to repopulate the halos with a galaxy of the size that we consider correct. And that will be coming from an almost semi-elliptic model that is inspired in observations. So this is what we did. We collected a sample of observed galaxies. In this case, this was coming from the Spark sample. So basically galaxies for which we had rotation curves. And then we did, so you can plot the stellar mass versus effective radius of those objects, and inspired on the distribution of how many of them are sort of low surface brightness versus high surface brightness. And you can see over here what is the fraction as a function of a stellar mass. Then we took all the halos that were infalling in our clusters, and we assigned, we know the stellar halo, the stellar mass from the object. We trust the simulation that much, but then we just corrected the size to be inspired by these observations. Of course, these observations are at redshift 0, so we needed to scale this with redshift, and so it was we added a redshift evolution, basically taking into account the redshift at which each subhalo is infalling. The next step is, of course, if we don't trust the infall structure of the objects, we also don't trust their size at redshift 0. So then what we did is to model what would be the stellar size of each of our galaxies. And we did that with also a semi-analytic treatment that corrects for basically the non-well-defined structure. So these are coming from models like Peñanurria and Navarro or Errani that are, so they are n-body models, very idealized simulation, super high resolution, in which you embed your stellar system into a NFW halo. And now what you can study is as a function of how much fraction of mass has been stripped, you can now predict how the size evolves, or how the velocity dispersion, or how the stellar mass of that object evolves. All right. So then the level of stripping is well constrained by the simulation. So we use this directly from the simulation. We take the information into the cluster, we take the final mass, and we know how much mass this object has lost. So once we have our initial size assigned, as I just explained, you can actually predict the final size and everything else. And from these curves, you can already have a hint of what is going to happen. So if you take an NFW and you really strip it off, provided the stars are quite segregated to the inner regions, what you find is that as you strip mass, the size almost doesn't change that much, but the stellar mass can change quite rapidly, especially once you are quite tidally disrupted. So this already gives you the idea that if you have an object with a significant size, and now you strip all the mass, but the size remains the same, that would be a channel for formation of UDGs. So once we applied our model for the initial sizes and also the tidal evolution, we found a dual origin for UDGs in these clusters. We found that there are UDGs that already infall as UDGs from the field directly. And those you can see here, if you plot them in the velocity dispersion versus stellar mass, you find them here and in the upper envelope of this, and you know that they have not formed, they have not lost mass because the color is quite orange or red, which means they have retained their mass mostly. But as tidal disruption evolves, you will see that your UDG will start to drop and be somewhere in the lower envelope of this relation. All right. So the gray is showing all the galaxies that are in the clusters, but are really not UDGs, and we are only highlighting the UDGs here. And so what we found is that we get a very good agreement with many of the observational estimates for velocity dispersion. However, these objects that are dark matter free, they are still difficult. So depending on exactly what measurements of the velocity dispersion you assume, you might maybe touch some of them, and suggesting that you could form UDGs by tidal stripping. But if the initial measurements of these objects presented by Van Dokkum are the correct ones, then it looks like it's quite difficult unless you have some sort of core in your dark matter halo. The good thing is, if you now have this population in galaxy clusters that is kind of dual, some of them were already UDGs and some of them are tidal, they will have very different properties. So you will have, for example, the radial distribution. Your tidal UDGs will populate the core of your cluster, versus the born UDGs will typically be living in the outskirts of your clusters. And also they will have very different accretion times. The tidal UDGs are early accreted and old and Of course, if you assume that the infall time is a proxy for the stellar populations, they will, of course, be much older compared to the born UDG bunch. Now, of course, the question is, that's great, but we didn't answer the question of how born UDGs form, and that is correct, and we couldn't do it based on Illustris or TNG 100, but we are now looking into TNG 50, which has much better resolution and a better ISM treatment for dwarf galaxies. And the good news is there is a population of UDGs that seem in reasonably agreement with the observations. And this is a work that Jose Benavides just introduced a bit in the video before, and we are writing up at the moment. Now, the question is, can we do any better to understand these objects? And one of the things is that we're not really doing a one-on-one comparison to observations. For example, when we measure the mass. So the mass in observations is measured through, I said, kinematics of globular clusters. So what we did is we used a globular cluster catalog run on Illustris. So this globular cluster catalog was created by Felipe Ramos from the house here, working with Mario Badi and Hernan Muriel. And so in this sort of catalog, of course, the simulation Illustris does not resolve globular clusters, but you can come up with a tagging method to assign particles that are dynamically consistent with globular clusters. And that's the work that Felipe presented in 2020. So you can see these tiny red and blue dots would represent globular clusters, red and blue, metal poor, metal rich. And around each of the galaxies, we find some of them are around in the cluster. So for this work, we worked only with those that are associated to our dwarfs. And so how do you estimate mass? Well, that's our friend, the spherical Jeans equation, in which you can deconstruct or get some information on the total gravitational potential based on the distribution and the kinematics of the tracer. In this case, the tracer is a globular cluster. Of course, nobody goes through this, 3D spherical symmetric, but there are kind of mass estimators that are simpler that people apply directly to the observations. That looks something like this. The mass within the half mass radius will be some sort of constant times the velocity dispersion squared times the half mass radius. And that's how exactly it's done in the observations. So we did the same. We did the exercise of mocking or trying to create mock observations of these globular clusters and then proceeding exactly the way that the observers do. And this is work done by our student at UCR, Jessica Doppel. So what you see over here, this is a dwarf galaxy, and in green, you can see globular clusters. And this is a Milky Way-like galaxy. And so the question is how, by measuring the kinematics of these green points, you can actually recover the true dynamical mass of the objects. And the problem gets more difficult for dwarf galaxies because they don't have a lot of globular clusters. So this study did a very careful job at quantifying how well you can recover the mass by using only, for example, a finite number of globular clusters. And what you see over here is that how well you recover that, the mass, will depend a little bit on your mass estimator for the sigma, for the velocity dispersion, but also on, for example, the prior, if you use an MCMC method. So if you add about 10 globular clusters, then your Jeans formalism will be kind of thumbs up, it's okay. But if you are below that you will be in the dwarfs and the low mass regime, you have to be a bit careful with systematic biases. For example, the RMS or the by weight estimates of sigma can bias you low, whereas the other one's high. So applying the same that the observers did to our sample of simulated globular clusters and UDGs, what we find is, so the colored over here are our simulated galaxies with the sigma now computed in the same way using the globular clusters and using an MCMC with a flat prior, exactly the same than the observations have done on most of the observations. And we can find some overlap, for example, DF44 overlaps with some of our galaxies, but our enigma was this DF2 and DF4, that very low velocity dispersion. And what we found is if you look at these dark colors are simulated galaxies that have lost a lot of the mass. You can here see that is color-coded by dark matter fraction. So these dark colors seem to overlap at least with the upper end of the estimates for objects like DF2. And if you look a bit in detail, so these objects that are sort of outside the 1 sigma relation shown here in cyan, they seem to have always, if they scatter low here, they seem to have a lower dark matter bound fraction. So it seems that to confirm, once we do the same treatment that the observers, that tidal stripping would explain these objects. Now, does it explain things like dark matter free, like DF2? Well, we selected all the objects in the stellar mass range of this particular dark matter free galaxy. Different shades here show different observational bounds on their sigma. And what we find is that some of our objects, these pinky points, seem to overlap with at least the upper end of the sigma estimates for DF2. These objects seem to have between 7 and 10 globular clusters, which is the number of globular clusters in DF2. And if this is correct, then DF2 had an initial infall mass of a few times 10 to the 11. And it has lost more than 95% of its dark matter mass. However, I wanted to highlight that this is only the upper end, and none of the objects seem to go as down as the first estimate of sigma by Van Dokkum team. So I am 1 minute over time, so I will round up here and leave you with my my summary slide, and I hope to see you on Friday for our discussion.